Hi, I'm Dr. Pariser, and I'm going to talk about the force between two wires carrying current. If I have a wire that's carrying current, I, first I'm going to calculate what the magnetic field from that wire is. I'm going to use Ampere's equation, which says the integral of magnetic field around the closed loop is equal to the magnetic constant times the current that's flowing through the loop. Now, how do you know that there's a magnetic field? Can you see it, smell it, taste it, touch it? No. The only way you can know that there's a magnetic field is if you take a charge and you move it in the presence of a magnetic field. And if you move it parallel to the flow of current, you will feel a force. That's how you know there's a magnetic field. So let's say I had a charge over here and I started to move it. If I started to move it, there'd be a force. Now, would the force be different if I was a meter above, a meter to the side, or a meter out? No, it wouldn't. The force would be the same. And so I could take this out of the integral and say V times 2 pi r would equal mu0 times I. And so the magnetic field would be mu0 I over 2 pi r. So what is the characteristic of this magnetic field? If you don't have a current, then you don't have a magnetic field. If you have a magnetic field and you double the current, you double the magnetic field. What happens if you're close to the wire? Then the magnetic field is very high. And what happens if you go away from the wire? The magnetic field is very low. And so now I'm going to say I have a charge and I'm going to move the charge with a velocity v. Okay, so there's a Lorentz force. The Lorentz force says that the force is equal to the charge times the electric field plus the charge moving with a velocity v across a magnetic field. If I don't have an electric field, the Lorentz force is equal to the charge times v cross b. Now, V cross B is something that delights mathematicians, and I can show you that V cross B is equal to I, J, K, V sub x, V sub y, V sub z, V sub x, V sub y, V sub z. And this is a 3 by 3 determinant, and you expand the determinant, and you do all this stuff. But for physics, we use the right-hand rule. This is V, this is B, this is the force. And so, if I have the Lorentz force, would be Q, the charge, times V, and this is B, mu0 I over 2 pi r. Now here's a very interesting thing. What is the dimension of velocity? Velocity is length over time. And so if I replace this and say the force is equal to the charge times the length times mu0 I over 2 pi r and t. Now so I replace V by length over time. And now if I say what is charge divided by time? Charge divided by time is current. And so a charge moving like this is a current, and I call this current I2. And so the force becomes mu0 times L times I2 times I1 over 2 pi r. So what kind of force is this? What kind of force is this? First, if you don't have any current, then you don't have any force. Second, what happens if you have 1 meter of current flowing? Then you have 1 meter, one force. What happens if you have 1,000 meters? then the force will be 1,000 times bigger. But the force between two wires carrying current is equal to the magnetic constant times the length times I2 times I1 over 2 pi r. And that's the force between the two wires. And the force looks like this. Wait a second. This whole analysis showed if this is V and this is B, then the force would be that way. What happens if I use this wire to generate the magnetic field? Okay, so by the right-hand rule, the magnetic field will be coming out of the board here. And so V cross B would be down. So if this wire generates the magnetic field, the force is attractive. Or if this wire generates the magnetic field, the force is attractive. What happens if the current is flowing in the reverse direction? Then from this wire, the magnetic field will be going into the board. This would be V, okay? This would be B, and the force would be repulsive. So when wires are carrying current in the same direction, there's an attractive force. When wires are carrying current in the opposite direction, there's a repulsive force. Thank you very much.